All right, so we have just a little bit more to cover on splitting. And then we'll be ready to start working problems and applying what we've learned. So let's look at some more complicated splitting patterns. And these are still all pretty well, resolved and excellent signal to noise and all of these kind of things. But let's see if we can pick out some patterns. And this one is already drawn out. The whole kind of splitting tree is drawn out for us already. But the approach that we might want to take here is that the first thing that we should do is we typically want to start at the outside, one of the outside edges. And we want to look at these first two peaks that we see, and we want to look at what we actually want to do is go all the way across and try to estimate the relative areas or peak heights of all of the peaks, right? Because the ratios between these peaks are going to tell us what type of splitting pattern they are, because we know that a triplet is a 1 to 2 to 1 ratio, and a quartet is a 1 to 3 to 3 to 1 ratio. So by looking at those ratios, we can get an understanding of where the splitting is coming from. So we've already done that on this case, and so, but if we look at these heights compared to the taller ones, we can kind of estimate that this is maybe 1 to 1 to 3 ratio, right? And then it just goes on. We really only have two peak heights as we go across, and they're all, 3 to 1, all the way across, 1s and 3s. So that tells us, first off, that this first splitting right here, because it's a 1 to 1 ratio, has to come as a doublet, right? It has to be generated as a doublet. And so everything else in here must be split as a doublet as well. And so what we need to do is figure out where those doublets are. So, we can see another symmetrical one on the other side. We can probably have a doublet here. And so sometimes what helps when I'll do it on a piece of paper is that sometimes I'll just, lay a paper down and make a mark on my paper. And then I can slide it across, and I can see exactly which peaks are the same distance apart. And so that kind of helps sometimes. But so in here there's a small doublet in here. There's one here. 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 And here.
So, at 0, we have, I thought, a doublet. That's not a doublet.
Right at 0, no, that's not actually a doublet there.
And we first determined that gap distance. How did we first get that gap distance?
Well, we look to the outside peaks. All right? And so we know, because these are a 1 to 1 ratio, they have to be generated as a doublet. So there has to be a splitting that leads to a doublet, because we have a doublet component right here. If it was a triplet, it would be a 1 to 2 to 1. If it was quartet, we'd have to have a 1 to 3 ratio at the outside.
And we wouldn't assume that's just two singlets?
Well, no, this whole thing is one signal.
Oh, okay. Gotcha.
Right, so this is only for, for a single signal. And it's split multiple times to generate this pattern. So what we're trying to do is figure out what the pattern, or how the pattern is generated, and what components generate that pattern. So we look out here first, and since we see this 1 to 1, we know these are doublets, and so what we would do is condense each of these doublets. All right? The one in the middle, we really know that this is not a splitting because there's nothing really else that matches that. Okay, so that That just happens to end up that way because of the other splittings. Okay, so in this, what they do is they bring these together, right? These come together. That's how the first doublet was. The bigger one is here, small one is here, big, you know, and so they're these 1 to 3 to 1. So now what we do, we could draw this out, but now what we're going to do is look at the ratio from here to here, because these are the new outside peaks. And because it's a 1 to 3 ratio, we know that that has to be result from a splitting of a quartet. Right? And so then this is 1 to 3 to 3 to 1. So that those peaks are giving us a quartet. So we bring all of them together. There's another quartet here, 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 and here. So we essentially have 2 quartets that are overlapped like this after we've, and then each of those peaks was split into a doublet. Okay?
This would be a doublet, quartet, doublet.
Right. So then we come back to these 2, and then we see our last peak here. That would be the one with no splitting. So yes, we have this component of a doublet and a quartet and another doublet. Okay, and if we wanted to figure out what the coupling constants were here, then we would have to look at the distances for these different components, or we'd have to find the different components in the spectrum. Okay, so the first doublet is the easiest one to figure. It would be just the distance between any of these doublets, right? And so if we could estimate this, so it looks like about maybe 4 hertz or so, right? Okay, the next splitting would be from one side of this to the next peak. So this is the quartet splitting, because this is the 1 to 3 ratio. Okay, and it has to be, you know, if there's 2 doublets here and we condense these to be quartets, it has to be from either the left side of this doublet to the left side of this doublet, or the right side of this doublet to the right side of that doublet. Okay? And so that would probably be, how much is that? 1, 2, 3, 4, 5, 6, maybe 7 hertz or so. And then where do we find the big doublet?
Between the 2 quartets?
Yeah, between the quartets. So we could again start clear on this side. And where do we find the left side of the other quartet?
Negative 2.5 hertz. That,
Negative.
like right.
Okay, so it's 1 to 3 to 3 to 1.
But they're overlapped.
1 to 3 to 3
Oh.
to 1.
Okay, I see.
They're overlapped.
Right? So it's going to be from the left side here to the left side right here. So it would be from there to here. You or from, you have to just make sure it's from the same component. So it could be from here to here, right, or from here to here, I think, or, you could measure any of those. And in fact, you should be able to measure those and they should match. So this is another place, if I had, I guess I could do this with this, if my paper is big enough here. It's not really big enough all the way there. But for maybe this quartet component, I could make a mark here and a mark here, and then I can slide it across and so I see, oh, those match, right? Those match, those match, those match. And so you should find those coupling constants should match all the way across. Now, from a practical point of view, when you have the computer pick out the peaks, so you can measure the distances, in theory, all of the coupling constants, either between this peak and maybe another peak that it was coupling to, the coupling constant should match, right? But if you do this numerically, sometimes they don't quite match. Have any of you done this before? So why would they not match? Okay, so sometimes J values do not exactly match. So for example, right, if we just had two doublets that were splitting each other, that this J should match this J. But when you measure them off the spectrum, they're a little bit off, right? They're not perfect like you think they should be. So why would that be?
The way they move around and solve it.
No, it's not really. The solvent shouldn't affect the coupling, the coupling constants, the distances.
Like as the molecule moves.
Yeah, but even if it did, then you're not going to change one coupling constant without changing the other. So because that process or that effect is felt by both of those protons. So it's really more of an experimental issue, more of a data sampling issue usually. Because if you, and try this one time, if you run a spectrum, pick out a big peak and expand it really big, right? And if you look at the peak, sometimes it will be, it's essentially created by a bunch of data points, right? And unless the data point, you have a data point that hits right at the very top of the peak, sometimes it'll go like this, and the top of the peak should be up here, but the way the data's been sampled, it kind of cuts across like this. There's just not enough data points to make the peak exactly right. And so the tip can be skewed just a little bit to the side. So it's more of a data sampling issue than that the coupling constants aren't, matching.
And this is the math part where the software knows to extrapolate out and not just connect the dots with links.
Well, I don't think that it really does. It can't find the tip unless there's a point up there. So, one thing that you can do, to help that a little bit is, you can change the number of points, data points, over which the spectrum is processed. So the Fourier transform. So, usually what happens, you can collect maybe 16K of data points. And that means that, your FID is going to here, and maybe the total number of points is 16K. And what you can even do, you can either sample over 32K, or what you can also do is just add another 16K of zeros after you've done your experiment. So they call it zero filling. And so then, when you do the Fourier transform, it's calculated at over 32K of points. And it helps fill in the points on the curve. And so that's something that can help as well. Yeah.
So would those 16K 0 point,
Mhm.
would that be dummy scans on the NMR? Is that what it looks
No,
like?
the dummy scans are more, those are scans that are done at the beginning of the experiment to allow the system to reach equilibrium.
Okay, that makes sense.
Yes. So this is more that you have a certain number of points that you actually sampled in your FID. So it could have, however many points it measured as it was going like this. Okay? Sometimes, I don't know, on the 500, maybe they always sample 32K now. And so you could probably zero fill even more. It's like, the faster the computers get, the more points and data it can handle, and certainly they're super fast right now. But yeah, it has almost the same effect of adding these zeros, so just increasing the data set after the experiment, then sampling, twice as many points during the FID.
And Topspin and ANOVA have really easy menus that let you change.
Yeah, I'm sure, right.
And I'm confused on how, I don't know if we talked about this yet, how the difference between 0 point and line broadening to weight the beginning part of the.
Yeah. I
Are they
think what we'll
connected or
do is we'll have Casey come in and maybe talk about some of that stuff.
Because they are different. Line broadening and
Right.
LV value in hertz is different than zero filling, correct?
Yes.
Okay.
Yes, definitely.
Okay.
All right, so let's look at another one already. Okay, so we're going to start at the outside, right? And we're going to just try to work our way across and estimate intensities. All right, so if we start with 1, next one's going to be 1. What do you think about the next one? Yeah, probably 3, right? 3, 3, 3, 1, 1. Right? So what's going to be the first splitting? A doublet, right? So we're going to bring these two together. These two together. These two together. And these two together. Right? And notice, if you're going to measure coupling constants, you have to, make sure you're measuring the right thing, right? Because, for example, the distance between these two middle ones, this is not really a coupling constant. All right? Or between, that one especially. Okay, so these are 1 to 3 to 3 to 1. So it looks like a quartet, right? So we had a doublet and a quartet. And so these are all gonna just go together into one. Okay, so this 1 to 1 is for a doublet, and the 1 to 3 is a quartet. So this is really what we had on the last one, you know, but then we had one more big doublet on top of that. Okay, so a doublet of quartets. So how, from a structural point of view, how would we generate a doublet of quartets?
Yeah, split by 1, split by 3.
Right, so we'd have to have, say, a CH3 and, say, a CH over here. And so we're observing this proton right here, right? So do you think this is a common situation, though, if you had a molecule like that, that you'd have one coupling constant to the methyl group and a different one to the other H?
It'd have to be very significantly different ones.
Yeah, so it could be, I guess, maybe if these carbons here were like part of a ring or something like that, you know, then those coupling constants could be very different. If this was part of a chain, then those coupling constants would probably become more similar.
Yeah, that's what I was thinking.
Yeah, so because we get more average coupling constants. So what would this pattern look like if the two coupling constants were the same?
More
Quintet.
Yeah. So then we'd have just 3 and 1 on the other side. We can still kind of map it out in the same way, though, as if we have split this, say, into a quartet, like this, and then the doublets would be the same size. And so when we split these again, they overlap. Right? So this is if J1 equals J2. And of course then on this scale up here we could measure those, right? We could measure one coupling constant between here and here. And then the other coupling constant could be from here to here. All right? But you can see even on this spectrum, you know, some of these peaks are more round or not as sharp. And so in those cases, it's harder for the computer to pick the tip, right? And so the values, because we get these coupling constants by measuring the difference between these 2 points in hertz. And so, you know, they won't be the same out to, you know, a whole bunch of decimal places or something. And so what you typically have to do is then take the average, and that's what you would report. All right, so let's look at something else, though. We've looked at chemical equivalence, which we talked about based upon symmetry or based upon doing this substitution, you know, substituting an H for a deuterium in one structure and substituting the other H and looking at the relationships and stuff. We're going to look at something that's called magnetic equivalence. Okay? Magnetic equivalence is when the chemical shift equivalent nuclei couple to other, or couple equally to other protons in the spin system. So what that means is that if these 2 protons are equivalent, they both couple equivalently to these other protons. Okay, so this J and this J equal each other.
That's how we get the quartet.
Yeah.
Right.
One.
Yeah, that'd be a quartet, yeah.
And that's what you commonly see.
Yeah, this is the common situation.
Yeah.
Okay?
So it's like 5.1 or something.
Probably not quite that far down, probably 4.1
4.1
or something. So magnetically non-equivalent is when we have chemical shift equivalent nuclei, right? They have the same chemical shift, but they couple unequally to other protons in the spin system. So for example, these two protons are chemical shift equivalent, right? Because there's a plane of symmetry down the molecule. These two protons are chemical shift equivalent, right? Because they have the same plane of symmetry. However, this proton is going to couple to this one with one coupling constant, right? The ortho coupling, 6 to 8 hertz or something. But this proton here can also couple to this proton over here, right? So it has kind of an ortho coupling and a para coupling to the same signal or same protons, right? So this J, if we call this J1 and this is J2, these are not going to be equal. And this is magnetic non-equivalence. And this causes more what we're just going to call second order effects. Right? We already talked about some second order effects when the chemical shift difference becomes, small or close to the same splitting as the coupling constants, right? And the outside peaks dropped off and they pointed to the inside, and if they got too close together in chemical shift, then the number of peaks could even get changed. All right? When we have these magnetic non-equivalents, this also causes some weird in the spectrum, which are difficult for us to predict. And I don't think any of the programs that I've seen where you're predicting the spectrum or simulating the spectrum also simulate these kind of effects. Okay, so for example, this top system, this parachloronitrobenzene, right? So they have these now listed as A prime, X, and X prime. So A and A prime should have the same chemical shift, right? So these two are chemical shift equivalent. X and X prime, they use an A and an X because they're pretty far apart in chemical shift. X, these are chemical shift equivalent. But the coupling between A and X is different between A and X prime, right? And likewise around the ring. And it starts to cause these effects. So if we didn't take this into account, what would we expect the A signals and the X signals to look like?
Two doublets or just?
Yeah, the simplest, kind of the classic paras. Substituted benzene ring is a pair of doublets. Okay, and this is what we, would see if it's a much lower field magnet and stuff. But, and that's what we mostly see, if we look at these two peaks here. But we've got all this stuff down here at the bottom.
They should think it's impure.
Yeah, right, you might think it's impure. But this is all resulting from this second order effects.
Yeah, that's super useful to know.
It's just kind of annoying, huh?
Here's
Yeah,
it's pure Lisa, I swear.
I can't figure out what that was.
And it's because of this magnetic non-equivalence. Now look at this other one. This is even worse. Because we have these two protons, right, that should be chemical shift equivalent. We have these two protons that are chemical shift equivalent. However, we have, the couplings that we see are, we have an ortho coupling here and a meta coupling here. Okay? And so we can't even say, if we could just see these couplings, the ortho and the meta, then we might think we just see a doublet of doublets, right? And that's a little bit what we see, right? If we just look at this, 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 and this, it looks like a doublet of doublets. But then there's actually extra splitting in there, and then we have these small things down below. So this is kind of like a doublet of doublets.
So, when you, in your experience, when you report a spectrum like this in the SI, do you usually explain it like that? Or just
No,
put it in there?
probably not.
No one normally does that.
Or just
Yeah.
put it in there when M
They
node
just call it
spits
a
out for
multiplet.
your...
Yeah, it might be a multiplet, or they might, because in reality, when you get these second order effects too, the chemical shifts and the splittings are not actually what you measure right off the spectrum either. The chemical shifts get skewed to one side, and
Why does it flip?
well, they're like mirror images almost, couplings, right? Because it's two sets of protons, right? So essentially, one of these is the blue protons, and one signal is the red protons, because they still have chemical shift equivalence, right? But it's a symmetrical system. Because then if we look at, say this proton here, it has its ortho coupling here and its meta coupling back over there. Right? So this just kind of throws a little bit of a monkey wrench into things.
Two doublets, right?
Yeah, and if you, if we had a system like this where we had two different groups here, well, then we'd see all probably all four would be unique then. They wouldn't even, there's no symmetry then. So we wouldn't have any of that problem. All right, so this is just a heads up to watch for this kind of thing. And do your best. All right, so let's, I just want to show you a couple of things about how the splitting patterns for signals. I think I probably changed this from what you guys have. I made it simpler. And so I want to just show you, we don't really have to draw this out, but I was using this website right here. It's kind of an interesting website. It has Proton, C13, even two-dimensional NMR simulations that you can do. You can draw in the structure, and it'll draw out a spectrum, and it'll even do it for two-dimensional experiments. So I'm not going to draw it here, but let's think about what we would see anyway. So this X and Y are just some groups that don't have protons, right? So we're limiting the coupling to what we've seen right here. And so what I'm showing is that essentially we have this trans coupling here at 17 hertz, so we get a big coupling constant there. We'd have a small allylic coupling between H1 and H3, and then we have like an 8 hertz from H1 to H2. Okay, so let's think of, if we looked at H1, what kind of a pattern would we expect? I guess we could draw these out. A doublet of doublets, right? It has couples to H2 with 8 hertz. So if this is 8, and then to H3 with 1.5 hertz. So it'd be some little small coupling like this, right? So we'd see a doublet of doublets. Okay, what about H2? Doublet of triplets, right? Because we have a big coupling, the 17 hertz. So we got a really big 17, and then we have 8 hertz, right? So half of that, so 8 is going to be somewhere in here. 8 and 8. Oh, but one of them has to be, that one should be triplets, shouldn't it? And so half of 17 is just, so it's almost going to go to the middle. Like this, right? Because 8 plus 8 is 16, and it's 17 in the big gap. So this would be a 1 to 2 to 1 to 1 to 2 to 1.
What are you, sorry, could you explain those long lines that you draw at the very end? Underneath H1 when you get to the, when you just said 1 to 2
Here?
to 1, 1 to 2 to 1, yeah.
Well, these are just lines that would be the peaks.
Oh, I see.
We got a 1 to 1. These are all doublets, so they're all equal. This is 1 to 2 to 1 because it's a triplet, 1 to 2 to 1. I'm just not trying to link them together because I'm not that good at drawing the actual spectrum. Okay, and then what about H4? Oh, H3. Trick question.
Yeah. Just a singlet. Oh, sorry, doublet with a
It'd be a double effect, really.
wide.
So it's going to be a doublet of 17 hertz again. And is that all? And tiny triplets, 1.5.
Oh, because that's 3.
Right, because it has the allylic coupling it too.
Okay, yeah. Okay.
So this is going to be 1 to 2 to 1 and 1 to 2 to 1. Okay? So these would be kind of what we would expect for the first order coupling. Okay, so what I did on this website is I thought I could do it on my iPad, but I couldn't get it to work, so I had to do it on my computer, and I just copied over some pictures. And I notice the chemical shifts here. So 1 I have down at 3 parts per million, and H2 and H3 have almost the same chemical shift, so they're very close together. All right, so that's going to create second order coupling. And all we're going to look at is these 2 protons. Okay? Right, it's this one here. These 2 in the middle have come very close together. Just because the triplet coupling constant is getting close to essentially half the size of the big doublet. Right, so the 2 triplets are just, we have triplets, and then the doublet component is what controls how far apart those triplets are. And those triplets could be, right now, they're just almost on top of each other. Right? Or they could superimpose there, or they could be inside like this. Right? It just depends upon the relative coupling constants. And what I've done, it's hard to see the green ones, is so in this program, so this is just simulating couplings. So what you can do here is, I cut part of this off too, this is like 1, 2, 3, 4. I guess I just took those ones out. So I just have 4 protons in here. And then I put in the chemical shifts, 3 and 3, these 2 are the same, right? And then, I made it 5.75 and 5.8. And then what it does is for H2 to H1, there's no coupling between these 2. Right? So this would actually be 1, 2, 3, 4 in this. right? And then between this one and these two, I have it at 8 hertz, right? And then from the next one over here back to these two, I have 1.5 hertz, and to this one I have 17 hertz. Okay, so you can build these up. Before I actually had a CH2 on this side as well, and that's why I had these two blanks, and so then these were both the same, and then they have to have other coupling constants. So you can build up, I think, up to 5 protons in the spin system. Okay, so what I also did is I calculated this out. You can change the magnetic field strength or the frequency. Okay, and so in the green, it's kind of hard to see, is what I calculated out for the spectrum at 300 megahertz. All right, and see, we see these peaks out here, and then it's a very second order pattern. It doesn't really even have the right number of peaks like we would expect. Okay, but when I went to 800 megahertz, we get these signals like this. Okay, so one of these, right, so this must be H3, right, because it has a doublet, it has the big doublet and the small triplets. Right, it's still second order because we see this slanting up like this, but at least we see the right number of peaks. And then for H2, we also had a doublet of triplets, but the triplets were bigger. Right, and so that's what we see here. Here's one triplet, and here's the other triplet.
Why is it not equivalent?
Why is what?
Why is it not equivalent in intensity, the two triplets?
You mean these two or these two?
Those two, right.
That's what I showed last time as far as that's the regular kind of second order effects, is that they start to point towards each other. Right, so for this blue one, you know, if we see this going in this way, pointing toward the inside one, that shows that these two are coupling to each other, or they're at least, and the outside ones get smaller and smaller as those chemical shifts get closer to each other. Okay, except at least we're seeing the right patterns in the 800.
Can I ask you,
Yep.
on the left of the blue structure, I would have called that a triplet. But you're saying the triplet, the peak furthest to the left isn't actually the triplet part. The triplet part is connected to...
No, it's a triplet, right? Because both of them, both H2 and H3 up there should be doublets of triplets, like we drew before. They both have the same doublet component.
Where's the doublet?
So,
This is the doublet,
the one on the
here
left and the one on the right.
and here. 17 hertz.
Only that explicit peak of that triplet peak.
There are 2 triplets on the right, they're just spread out. because
These are
of the
2
doublet.
triplets. Here's a triplet and here's a triplet. This is one signal, a
Yeah.
doublet of triplets.
This one, and this one, that's a triplet.
Yes, correct.
But then this peak right here and this one is a doublet?
No.
Which one is the doublet?
This is a triplet and this is a triplet, and the splitting of those triplets apart from one another is the doublet.
Gotcha.
So if we were going to measure the doublet here, we could measure it from the small left side to the small left side here. We could measure it from the tall peak to the tall peak, or to the small right side to the small right side.
Okay.
All of those should match.
Okay.
Okay? On this side, it's also 2 triplets, right? A doublet of triplets. We could measure that from the left side here to the left side of this one down here. Because here's one triplet, and here's the other triplet. And they're almost overlapping in the middle.
So even though it hits the baseline, it's still a triplet.
Yeah. right? So it's kind of like, we can go back to this other one. Okay? Okay, so why is it that, when I set this up, both of these protons have the same chemical shift in the green spectrum and the blue spectrum. But look at how the green spectrum goes way out here and way out to here on this side. Why does it have such a bigger range of chemical shift?
I think it's because of that way O, J is different, right?
You mean, because the scale, you mean, or
Yeah, I think.
because it's divided by the magnetic field strength, the frequency? Right, exactly right.
Yeah.
Because so the chemical shift in hertz depends upon the magnetic field strength, right? But the coupling constants do not. Okay, coupling constants do not depend upon the chemical field strength. So this 8 hertz coupling is going to be 8 hertz no matter what the chemical shift, the field strength is. Okay, but when we go over here, because at 800 megahertz we have 800 hertz in every part per million. Right, so there's a lot more hertz, and so the size of a coupling constant gets very much smaller relative to the total number of hertz in that part per million. So it kind of squeezes everything down, resolves our signals, because look at here, they were almost overlapping in the green, but now they're well resolved from one another.
So if we experimentally made this molecule, and then we wanted to compare it to literature values, but we have an 800 megahertz and they have a 300 megahertz, our peaks wouldn't match. So if they said they reported a peak at 5.85, we wouldn't see that peak in our 800 megahertz. So we would have to look at the J coupling.
Well, they wouldn't report this one out here at 5.85 because that's only one component of this signal. Right, the chemical shift would still be in the middle of this whole, there's in the green, there's still kind of a doublet of triplets going on here.
So which point would you pick to report in our paper?
You take the middle point of that doublet of triplets, just like this one, we pick a point we'd maybe take this peak and take the average value of those two, and it would be right down the middle. In the green, it's also a doublet of triplets. Let's see if we can see it. So here's kind of like a triplet, though it doesn't look really symmetrical to me. And here, here, and here is another triplet. Okay, so these triplets, and they're much steeper sloping here because it's much more second order at 300 megahertz than it is at 800. So again, you take the tip of this one and the tip of this one, and the chemical shift would be somewhere in the middle of those two. So the chemical shift should be the same.
Okay, because normally what I do is I pick peaks, and I pick like the top of a peak and call that what I report, and that's what I compare to literature values. That's not what I should be doing. I should be finding that average.
Yeah.
My triplets are.
Well, you should be finding kind of the middle of the signal. Right, so if you, from a simple point of view, if you have a doublet, you're not going to report this as the chemical shift, or this, you're not going to report both of these as separate chemical shifts. If this is just one doublet, you take the chemical shift is going to be here, right? So you have to take the average of those two peaks and to get the chemical shift, right? If it's just a triplet, right, then you can just take the tip of this peak, right? Or if we have this doublet of triplets, we take the one in the middle of both triplets. Even though when it gets second order like this, really, the chemical shift is not exactly in the middle of that signal anymore. The second order starts to skew it off to the side a little bit. Let's see if we can see that. So this one should be right at 5.8 is what I put in for that signal, right? And 5.8 is right here, and that's closer to the bigger peak than it is to the small one, right? But I think from an experimental point of view, at least the way I've always done it too, and maybe I'm wrong too, but all you can really do is report the average value in the middle there.
Yeah, there's something that come into my mind where we're trying to compare two like papers,
Mm-hmm.
and I'm wondering if you may have just figured out something that we may have
Oh,
seen.
uh-huh.
Yes.
Yeah,
That's what I'm wondering.
Yeah.
I don't know if that's actually
we were
correct.
very confused as to how they, but,
Maybe it's how they report.
yeah,
Yeah.
okay.
Okay.
All right, let's go now. Okay, so let's just look at a spectrum here. This one has all of the, well, it doesn't have, it has a structure there. Let's see if we can assign this. Lots of peaks, but look at how they're all pretty well resolved and everything. So look at the structure, and then the spectrum here is just solvent out here. If you look at that structure, which of the protons do you think would be the easiest to assign onto this spectrum down here?
1 and 9.
1 and 9. Okay, where are we going to assign those?
At 750?
At where?
PPM or
70 hertz.
Sorry, 750 hertz?
Yeah, the
Yep.
one on the top right.
it just
Yeah.
Well, no. So the ones in the expansions go in order. So this one here is this doublet of doublets. This packet here is this. This one is this. This one is this.
2.5.
So the question is 1 and 9 equivalent? They look pretty.
No.
They look like they're pretty close.
Well, where are they going to be in the spectrum?
2.5.
1.5.
The lowest.
Yeah.
Clear on the right
Right
side
side,
over
yeah,
here,
yeah.
right? So that's going to be these.
Oh, so if you put the two chunks like
Yeah,
that.
so they've just gone left to right.
Okay.
As you can see, as the frequency goes down, right? So they put these in hertz here, so I think you could maybe estimate the size of the coupling constants if you wanted to. Be easier to interpret it if they just put parts per million up along there, and then you'd know right off the bat which ones are which.
It's the same size.
Yeah. So this has got to be it. So is a triplet what we would expect for 1 and 9?
No.
No.
But it's the rotation.
What would we expect in a simplistic point of view?
Doublet.
A doublet, right?
The big one.
Solvent you're showing the road.
Over here,
Could be under it.
this is what they just did they changed the solvent. So in chloroform, it looks like a triplet right here. And then they started adding some deuterated benzene into the solvent, and look at that, those, there were two doublets that split apart.
The triplet doesn't look equivalent if you look at it.
Yeah.
Is one slightly larger?
Yeah, one's slightly a little taller than the other.
So,
Is it because as it rotates around, the OH?
Well, why? So clearly,
it's just a-
these two methyl groups do not have the same chemical shift. They're not equivalent, right? So why is that,
The OH.
right? But is it why? What about the OH? No, it's not rotation around here.
The shielding of the lone pairs on those protons.
Well, why does it affect the two methyl groups differently?
Proximity, when one's closer than the other. I mean, that bond should freely rotate.
That's fine, yeah.
But if it freely rotates, it still is gonna.
Hydrogen bond is
Well,
Yeah.
No, I don't think any of those reasons explain why it affects one of the methyl groups differently than the other.
Is this something to do with, no.
It affects both the same, but when it's on one side, it's different than the other side, so you have to account for those.
Yeah, but why is that? Why is it different on one side than the other side?
Because the shielding of the proximity to the OH group is going to be different than the shielding in the proximity to the CH2 group.
Yeah, but it's just a carbon chain, right?
Well,
Usually, why is it, usually when we see kind of an isopropyl like this, those methyl groups are the same. Why is it in this case they're different?
It's a solvent.
No? No, the solvent changes their chemical shifts, and just luckily, by adding some benzene, they move apart. You can't really predict that, but you can just try some different solvents sometimes, and they'll move things around a little bit, and sometimes they'll be apart, sometimes they'll be right on top of each other.
Is there some, this
So
is,
you look down that bond, I mean, like, it's kind of locked in one conformation, so one side is interacting with the OH more than the other.
Well, that's not a benzene ring.
No, but it's still,
No.
does it have something to do with the bond angle or something? Because if there's,
Well,
I'm trying to remember if there's an effect like.
Well, okay, so let's
Yeah.
go way back to talking about chemical shift equivalence. All right? And what if we did that kind of substitution thing that we did before? We substitute for deuterium on one and substitute for deuterium on the other, and then we compare the structures. So what if we traded all three of these in for deuterium, and then we traded all three of these in for deuterium, and we compared those two structures.
Separately, like one will be deuterium?
Right, on one
Okay.
molecule we change these, in another one we change these, and then we compare the two structures. What would their relationship be?
An antio- no. What's the word?
Would they be superimposable?
Technically no. Because it-
Right, because if this is CD3, this is CH3, and there's an H, this has become a chiral center.
I'm trying to remember.
Do we have another chiral center?
Oh, the one behind it. Three, you can change that.
No, it'd be
No.
seven.
This is a chiral center right here,
Yeah.
Yeah.
Oh,
right? They haven't shown us the chirality, whether it's R or S, but we have one chiral center here. We've then created another chiral center here. So what's the relationship between the two molecules when we do these different substitutions? They're diastereomers. And so these two methyl groups are, what's their relationship then? Diastereotopic. Diastereotopic protons have different chemical shifts. So it's because of the chiral center here. These two methyl groups are in a different environment. Okay, in a diastereomeric environment.
because it doesn't give you specific stereochemistry, so we assume that it's,
Well, that carbon has 4 different groups on it, right? So it has to be chiral.
right.
Doesn't matter what the chirality is, or even if you had a racemic mixture, right?
Would it be the same if there wasn't a racemic mixture?
If it was a racemic mixture, it would still be the same. You just have 2 mirror image compounds, and enantiomers behave the same in an achiral environment.
But if we had one stereoisomer, would that have been a doublet?
No,
It'd have to be equivalent.
right? Because if you have R chirality here, then you have 2 signals. If you have the S, you'd have 2 signals as well. Maybe you could say if you had 1 and 9, then it would be 1 and 9.
Okay.
Right, they'd be switched, but it would give you the same spectrum.
So it's due to the fact that we have a chirality center.
Yes.
See, even though the chirality center is 1, 2 away,
Yep,
we still see a change.
yep. These two are diastereotopic topic. So they have two different chemical shifts. I shouldn't draw it like that. It's not a coupling, right? Let's draw it like this. So they have different delta values. Okay, so you're right though. These are the two. These are 1 and 9.
That's 300 or the 750?
The 300.
No, I'm looking at the big triplet.
Yeah, the
Here,
300.
1 and 9.
Yeah, gotcha.
I was looking at the big spectrum.
Oh,
This one. Okay, so we've assigned, took us 10 minutes to assign the methyl groups. Okay, what else can we pick out easily?
we thought that one was easy.
Yeah, good point.
The farthest one away.
Yeah, usually the one that's furthest downfield we should be able to pick out, right? Which proton does that go to?
7 because it's between
This one here.
sandwich between two double bonds.
7.
Yeah.
Yep, I'd go with that, but I would, yeah, it might be based upon chemical shift, but does it fit the coupling as well?
I
For H7, how many splittings would we expect? Right, we have 2 protons on C8, so we'd have a cis and a trans coupling, right? And so we should get a doublet of doublets, right? So I would agree, this is H7. Okay, now the other double bond protons all kind of overlap a lot. Okay, and so one thing that we could do, would be to do that trick that I had mentioned. As long as I think that as long as they plotted everything at the right scale and everything here. So we could look at this, and let's say we wanted, I'm going to pick out the trans coupling, so the bigger coupling constant. And I'm going to slide it over here and see what matches. And so see, this one matches right here. Okay? So that means that this proton has to be on C8, and it has to be the one that's trans to C7.
Could you do that one more time?
Because this is a doublet of doublets. The big coupling is going to be the trans coupling. The big coupling here, every other peak, is trans. And that matches this one. Okay? So we could say that this here is going to be H8, and it's going to be trans to H7. Okay, now the other ones are all overlapped, so they're kind of more challenging to find. Let's just mark the smaller coupling constant here and slide it over and see if we can match anything. So that one doesn't.
So,
Huh?
the integration of H7 should come out to be 1, and then the integration of where we just marked H8 should come out to be 2?
No. That should, here's the integration down here, right? So here's 1, and for these 2 peaks, that's the integration here. It's the same.
But doesn't H8 have 2 protons?
No, H8 has only, it does, but we've only assigned one of the 2 protons so far.
So the trans...
Right, because,
Oh, yeah, the other one is.
right, because that double bond is like this. If this is 7 and this is 8,
Oh, we don't want-
right? One of H8, this is what I'm calling H8 trans.
Oh, there's a H6.
And then we have H8 cis.
And even though we only have 1 proton for H7, we still see that splitting pattern. that's why we still.
Right,
say
because
trans and assist.
It's couples to both of these, right? So it gives a doublet of doublets.
Okay.
Now, I think the intensities here are not the same, though, because notice here that this peak is taller than this one over here. It makes this look too small compared to that. But in fact, they integrate this, what I just said, is H8 is the same integration as this one. Right, I think they just plotted everything so they were kind of the same height. All right, so we were looking at the small coupling here, which has to be the cis one then. And so we slide it across, doesn't match that, doesn't match that,
Those two.
kind of matches in here.
You're supposed to use this.
Okay, at least something in there has to be the H, but I think that there's more overlapping than just this too. Okay, so something in here is H8 cis. Okay, and then what about the other double bond protons? We have we have 10 as well. So what kind of patterns would we expect H10 to be?
Geminal.
They're geminal, right? And so how does that influence their coupling constant?
This one?
What do I have here? Is it geminal coupling? Is it small or big or? It's small, yeah. So I think we're going to see those mostly as being singlets almost. So I'm not 100% sure here whether, let's see.
Look at that one next to the H8.
I think this is one of them.
Yeah.
This is one of the H10s. And then I think probably the other H10 might be overlapped right here. Right, so H8 is here, H10 is on top of that, and the other H10 is over here. That's my guess. All right, so we got all of the double bond protons then. What's the next easiest to assign?
CH4.
I was gonna say CH4, probably the next one.
Right, the H, yeah, 4, next to the oxygen, right? Where's that going to be?
Choose.
It's like the 3. I would say it's probably the 3.8 because look how
This, yep,
big it is.
right, so this is going to be H4, right? Because it's next to oxygen, so it has to be, it's a 3.8.
Just the whole, the splitting is just crazy.
Right, so it,
That's kind of where I was going with.
yeah, look at that splitting there. I think, yeah, well, we'll talk about that in just a second. Here, let's see if we can finish this by the end of today. All right, so let me just point out some other things now. So the rest of it are just the, just the CH2s. So we got a CH2 at 5, a CH2 at 3, and a CH at 2, right? So we have all of those, and they're all just, they don't have any functional groups on it. So when I look at this spectrum, I see this pair here, and unfortunately they're split between here and over here. But notice how those two are pointing towards each other. If we draw the arrow to the higher side. So what that suggests is that these two are a diastereotopic pair of protons. This is one CH2 group. Likewise, these two are a diastereotopic pair of protons. Okay? And then the one in the middle is not, because this one is nice and symmetrical. So the one in the middle is H2. All right, so that's here. This is H2. And then what do you think? So we have the two diastereotopic pairs. And so those are going to be the two CH2 groups that are next to where the alcohol is, right? And they're both affected by the chiral center, just like we saw for the isopropyl, right? So which of these two, 5 or 3, is going to be more downfield?
It's that way. 5 is at 11:50, I think. Hertz.
5 is the one that's more downfield.
5 is more downfield, right? Why?
Double bond.
Because it's a lilic, it's next to the double bond, right? So these two are H5. That makes the,
H3 is also a little.
No, it's not.
no, it's
I
not.
thought it was connected to.
Oops.
Oh, it's not connected.
Yeah, that's really
Okay.
bad.
Yeah, it looks like it kind of.
Yeah,
Okay.
right. It's not a
That makes
ring.
sense.
It's not a ring.
I thought we were looking at a benzene ring when we first started,
Yeah.
so, or something, it's changed a lot.
Yeah. So look at the integration for, and look at the signal for H2. All right, and look at this. It looks like it's integrating for twice as much as these other ones.
It's just 1 per.
So why is it integrating for so big?
For H2?
Yeah.
The integration looks okay because the integration for each of the H5 and H3 peaks should be 1.
Right.
But but 2 is.
But H2 is only 1.
Oh.
One
Is it exchanging with the hydrogen?
Well, is that carbon going to exchange?
Probably not.
No, never.
I'm not sure.
Is there any proton in this whole molecule that we haven't assigned yet?
Oh, the oxygen.
No.
The
Oh,
OH. Yep. So I think the OH is also hidden under there. We can't really see it. And it can move around, right? So it's kind of probably just a broad peak underneath here. Okay, so if we go back and think about the splitting of this, of H4, right, next to the alcohol, we said, oh, look at how complicated it is. But really what it has to be is because it's going to couple to 4 protons, right? And each of those 4 protons are non-equivalent. So it really should be a doublet of doublets of doublet of doublets. It should be 4 doublets. But some of those coupling constants are the same, and so they're kind of overlapping and reinforcing each other. So I'm not going to draw out how that comes out. We could probably go into that simulation program, right, and vary some of those coupling constants and try to reproduce that. All right? So kind of some of the take-homes here is, some of the things about the double bond protons, right? We have, bigger trans splittings, smaller cis splittings. Geminal couplings are very small, right? And then identifying these diastereotopic pairs of protons is important because if you've done many of these, you look at these, you're like, oh, those two must go together, and these two must go together because of the way they're kind of slanting towards each other. All right? You're looking kind of blank there, Stephen.
The beta diketones, when they look like that.
Uh-huh.
So I'm trying to look at my products from the photodegradation because I have a lot of things that look like this.
Huh.
And then there are things that look like triplets that I don't think are triplets, but I don't know how to explain it. But now this throws a huge wrench in that because I have no idea how to interpret it myself. I'm not really sure what to do at this point.
Yeah. Yeah.